Oh, in this video, we are going to take a look at some examples of actually using the alternating series test. So recall, an alternating series is a series that just switches terms back and forth between positive and negative. And then the test says, look at the part that's not alternating. Look at that b sub n. If the limit of the sequence b sub n goes to 0, and the sequence b sub n is decreasing, this means that the alternating series a sub n will converge. Now let's take a look at a few examples of this. The first example we are going to look at is the example of n equals 1 to infinity of negative 1 to the n minus 1 times 1 over n. This is not quite the same series we saw right at the beginning. This one is a little bit different because the exponent changed. Before we had negative 1 to the n times 1 over n. Now we have negative 1 to the n minus 1. All that does is changes what we start with, a positive or a negative. So this will start as 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5, and so on. Just because the exponent has changed, the name is still the same. This is still the alternating harmonic, because we have the harmonic series that alternates between positive and negative. So using the alternating series test, we want to identify the non-alternating portion. So the non-alternating portion, b sub n, is the 1 over n. So this is what we're checking properties on. First, does the limit as n goes to infinity of 1 over n equals 0? Without a lot of work, there is really not any work to be done here. This is growth rates. Yes, this is true. This goes to 0 because that denominator keeps growing. And then 2, is b sub n decreasing? And there's a couple ways to check these for this one. What is really nice is because it's so simple, we can just say, if I'm looking at the next term, n plus 1 is bigger than n, this means that when I take the reciprocal of these, 1 over n plus 1 is less than 1 over n. This is the term b sub n plus 1. This is the n plus 1th term of the sequence. This is the term b sub n. So yes, b sub n plus 1 is less than b sub n. So yes, it is decreasing. The other thing we could do is, instead for 2, we could use first derivative test. So we'd be looking at the function 1 over x. And the first derivative of 1 over x is negative 1 over x squared. And our critical point is 0. That's the only place that function is undefined, or 0. And we don't care about the left-hand side of this because we only care from 1 to infinity, right? We only care from here onward. But when I plug in a positive number, like 1, I still have -1 over something positive because of the square. And so -1 over something positive is still negative. So f prime of x is negative for x greater than 1, meaning f of x is decreasing for x greater than or equal to 1. So b sub n is decreasing for x greater than or equal to 1. So we can use the first derivative test as well. And unless it's about 2-3 lines like this one was, I would recommend using the first derivative test to show decreasing. So we have that its limit of b sub n is 0, and we know that b sub n is decreasing. Therefore, I'm going to erase this part of the b sub n, decreasing, and say, yes, this is true. And so the series -1 to the n minus 1 from n equals 1 to infinity 1 over n converges because both the properties are met by the alternating series test. In this case, for the sentence, the reasoning is these two statements. And so since we have shown them in our work to be true, we don't need them in the sentence. But we have our series converges or diverges by the test. So what this means for us as we move forward, the alternating harmonic converges. And so if we ever see the alternating harmonic, we can say, I know that converges. All right, next example is -1 to the n plus 1 e to the 3 over n. We wrote out some terms for this in the previous video. This looks like e cubed minus e to the 3 over 2 plus e to the 3 over 3 minus e to the 3 over 4, and so on. Now, two properties to check. We look for b sub n. B sub n is e to the 3 over n. It's the part without the -1 to the n, and it's also just a sequence. It's not a series. So we don't have the series notation, and we don't have the alternating. For the alternating series test, we have two properties to check. The first is the limit as n goes to infinity of b sub n. We want to check, is this 0? Well, this limit is the same as e to the limit of 3 over n. And 3 over n, as n goes to infinity, goes to 0. So this is e to the 0, and anything to the 0 is 1. That means the first property is not met. Going back to our series test, if the two properties are met, then the series converges. However, the alternating series test cannot prove divergence. So the first property failed. So we already know the alternating series test is not working. However, This is why we check this property first, because it is the divergence test in disguise. Because if this property fails, meaning the sequence does not go to zero, we can turn our attention to the divergence test. And the divergence test tells us to look at the limit as n goes to infinity of the whole sequence, so with the alternating part. However, what this alternating part is doing is it's just switching the sign between negative and positive. We know this e to the 3n is going to 1, so this whole limit, as n gets really big, this sequence is going -1, 1, -1, 1, -1, 1. It does not zero in on a particular number, it's bouncing between two, meaning this limit does not exist. Since the limit does not exist, that is not equal to 0. So by the divergence test, -1 to infinity of -1 to the n plus 1, e to the 3 over n, diverges by the divergence test. Okay, so if that first property of the alternating series test fails, look at the divergence test next. Okay, so let's take a look at another example. We have n equals 1 to infinity of -1 to the n plus 1 of n squared over n cubed plus 4. The sequence we're looking at is the part without the alternating. So n squared over n cubed plus 4. This is a positive sequence. So first we want to look at the limit as n goes to infinity of b sub n squared over n cubed plus 4. And yes, a lot of times these don't need much proving. We know this limit is going to be 0 because it's a rational where the degree of the denominator is bigger than the degree of the numerator. So the limit is 0. Second, is b sub n decreasing? This is where we're going to use the first derivative test. So our function is x squared over x cubed plus 4. The derivative using the quotient rule is x cubed plus 4 times 2x minus x squared 3x squared all over x cubed plus 4 squared. This function, when you multiply everything out, will become 2x to the 4th plus 8x minus 3x to the 4th, which is also all over x cubed plus 4 squared, which is also x times 8 minus x cubed, all over x cubed plus 4. X cubed plus 4 is never 0. This does not equal 0. So for our critical points, we'd be looking for where is x cubed plus 4 equal to 0? This never happens. And we'd be looking at where does 8 minus x cubed equal 0? Well, these happen when x equals 0 or when 8 equals x cubed. The cube root of 8 is 2. And I'm actually going to back up and fix something I said in a second. I actually said x cubed plus 4 is never 0. I said this because I was thinking about only positive values of x, because we ultimately, since we're looking at a series, only care about positive values of x. There is actually a value of x that makes this 0, and that would be the cube root of -4, which is a number we can find. We can take the cube root of a negative number. So this does exist, it's just negative. So fixing that, clarifying that, we do have a critical point from the denominator. It's just not one we care about. So we have 3 critical points. We have the critical point of x cubed, or the cube root of -4. We have the critical point of 0, and we have the critical point of 2. Like I said, we don't care about x being negative because we're looking at a series. So we don't care here. We don't care here. We do technically care about between 0 and 2, slightly. We care enough to make sure 2 is not the point that makes the denominator 0. And it's not. We know it's this value, which we don't care about. But between 0 and 2, if we plug in, say 1, we'd get 1 times 7 all over 25, or 7/25. That is a positive number. Between 0 and 2, our sequence and our function is increasing. However, that's not, again, not really what we're worried about, because that's increasing, but the alternating series test has some phrasing that I will go point out after we finish out this sign chart. So from 2 to infinity, say we plug in 3. If I plug in 3, x is positive. 8 minus x cubed would be 8 minus 27. That is negative. And then 3 cubed, 27 plus 4 squared is positive. Positive times negative divided by positive is a negative number. So there's our sign chart. We have a spot where we're increasing and we have a spot where we're decreasing for x greater than 0. And which one do we care about? I'm going to go back up to the wording of our alternating series test, and it says b sub n is decreasing for all n greater than some value. So just because it doesn't start at 1, that's okay. We just need, from some point onward, this is decreasing. So we know for our sequence we're looking at, the some point onward is after 2. So for x greater than or equal to 3, it doesn't start at 2. 2 is a maximum. It's not increasing or decreasing at 2. So for x greater than 3, our derivative is negative. So v sub n is decreasing for n greater than or equal to 3. And that derivative being negative implies the function is decreasing. So first derivative test worked. Had a few things we needed to worry about, but in general, from 2 onward, or for values at bigger than 2, our sequence is decreasing. So yes, this is true as well. The limit is 0 and the sequence is decreasing. So the series converges by the alternating series test. Right? Let's take a look really quickly at one more example. And that is this example of the series n equals 0 to infinity of sine of n plus 1/2 pi all over 1 plus the square root of n. This is another situation where we don't have a negative, but sine can be negative. So that might be what's making this an alternating series. So writing out a few terms. If n is 0, we get 1/2 pi inside of sine. So sine of pi over 2 is 1 over 1 plus the square root of 0. When n is 1, we have 3/2 pi inside of sine, and 3 pi over 2 is the bottom of our unit circle. Sine is negative. We had pi over 2, 3 pi over 2, and then when n is 2, 2 plus 1/2 is 5/2. 5 pi over 2 is the same as pi over 2. So we have pi over 2, 3 pi over 2, 5 pi over 2. So this would be plus 1 over 1 plus the square root of 2. And then one more, when n is 3, 3 plus 1/2 is 7 over 2. So we have sine of 7 pi over 2. 7 pi over 2, sine is back at the bottom of the unit circle, so we'd have minus 1 over 1 plus the square root of 3. So plugging in those values, we see that n plus 1/2 times pi is the inputs that make sine switch back and forth between 1 and -1. So this series is the same as -1 to the n over 1 plus the square root of n, starting from n equals 0 to infinity. So we do have an alternating series. Our sequence is 1 over 1 plus the square root of n. First, is that limit 1 plus square root of n 0? Yes. The denominator is growing and it goes to infinity. So the whole fraction goes to 0. Is b sub n decreasing? And we could use the first derivative test here. I would encourage you to practice that. I am going to show that same method that we used on the alternating harmonic example, though, where what we do is we say, I am looking at the next term in my sequence. I know n plus 1 is bigger than n. And my goal is to make this look like b sub n, which is 1 over 1 plus the square root of n. So step by step, I'm going to make this n look like 1 over 1 plus the square root of n. And what I do to one side, I'll do to the other. So first, I'm going to take the square root of everything. Square root n plus 1 is still bigger than the square root of n. All right, square root of 3 is bigger than the square root of 2. Next thing, I'm going to add 1. 1 plus the square root of n plus 1 is in fact still bigger than 1 plus the square root of n. Add 1 to both sides. Now, take the reciprocal, 1 over 1 plus the square root of n plus 1, and 1 over 1 plus the square root of n. Okay, we made this side look like that side. However, what just happened is when we take the reciprocal, the sign switches. So this tells us on this right-hand side, we have b sub n. On the left-hand side, we have b sub n plus 1. B sub n plus 1 is less than b sub n. So yes, this is decreasing. Both the properties are met, meaning the series n equals 1 to infinity of sine of n plus 1/2 pi over 1 plus the square root of n converges, because both properties are met, by the alternating series test. There are 4 examples of using the alternating series test.